Welcome. Today is Wednesday, December 13th, 2017, and this is the NHERI Early Career Researcher Forum. This forum is intended to foster the exchange of ideas and be a platform for best practices for successful research. It is intended to highlight compelling research, build up the natural hazards engineering student community, and provide presentation opportunities. For more information, visit the NHERI website at DesignSafe-CI.org, where you can find links to the SimCenter and the NHERI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructure's Simulation and Computational Modeling Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in the webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today's presentation is by Majid Abad Sechani. He is a PhD candidate in the Civil and Environmental Engineering Department at Rice University. Since starting his PhD at Rice, he has been studying the seismic risk to concrete dry cask structures used for storage of spent nuclear fuel. His advisor is Jamie Pageant, and the title of his presentation is High Performance Computing Aided Seismic Risk Assessment of Vertical Concrete Dry Casks. Majid, I invite you to begin your presentation.
Thank you, Matt, for the introduction. First, I want to say hello to all our participants and thank you for your interest and time. And I also want to thank SimCenter for this opportunity. Today I will talk about my research project, which is about seismic risk assessment of vertical dry casks, which, as you said, are used for the storage of a spent nuclear fuel. At first, I will talk about the motivation behind this study. Then I will walk you through seismic analysis and tip-over analysis. And then I'll briefly mention the role of HPC in research projects like mine. And then I will finish with conclusions and future work. So currently about 20% of the electricity in the United States comes from nuclear power plants. And safe storage of spent nuclear fuel is a very important issue in this industry. The storage process usually has three major steps: short-term storage, interim storage, and long-term storage. For short-term storage, special pools are used, which are called the spent fuel pool. In these pools, the spent fuel is kept below water, and water circulation cools down the fuel, and it also acts like shielding for the radiation. The spent fuel has to remain in these pools for at least 5 years before it's transported to interim storage facilities. For the interim storage, independent spent fuel storage installations, or ISFSIs, are used. The structure which is used for the storage is called dry casks. There are two major designs of the casks. One is horizontal rectangular models, and the other one is vertical casks. In these structures, flow of air cools down the fuel, and that's why the structure is called dry cask. My research is about vertical concrete dry casks. The structure looks like what you see in the picture. It's a vertical cylinder made of reinforced concrete. It has a mold, which is called liner, and it is used basically during the construction phase and remains with the structure. The cask receives the fuel in a steel canister. The steel canister is loaded at the location of the pools, which I talked about before, and then it's sealed and transported to the location of the casks. And then the canister is inserted into the cask, and it remains there. The vertical casks have air vents on the bottom and on top, and airflow through the bottom of the cask and then exiting from top of the cask cools down the structure, cools down the spent fuel. Currently, there is no long-term solution for the storage of spent fuel in the United States. And because of that, these structures have to be in service for long periods of time. So aging is a threat to these structures. In addition, since the structure is not mechanically attached to its foundation, under lateral loads, it might display different modes of motion. Specifically, it might rock, which causes angles of rotation, or it might slide or wobble. By wobbling, I mean a motion in which the cask tilts slightly, and then it spins around its longitudinal axis. It causes a horizontal displacement for the structure. So the rocking causes angles of rotation, and sliding and wobbling cause horizontal displacements. In 2011, an earthquake happened in Virginia. The magnitude of the earthquake was 5.8, and it hit a nuclear power plant. Although the earthquake was not very high, did not have a very large magnitude, some of the casks on the nuclear power plant moved, and the motion of some of them reached about 5 inches or 10 centimeters, and it raised many questions about the safety of this storage option. So the final goal of my project is to estimate the seismic risk to the vertical dry casks. And to do that, I need to answer questions like the probability of seismically induced large motions. I also want to know what happens if two adjacent casks hit each other because of large motions, or what happens if a cask falls down and hits its foundation. In this presentation, I will talk about the seismic analyses and the tip-over analyses. Moving to the seismic analyses, this is my workflow. It has 5 major steps: experimental design, finite element modeling, and then metamodel development, fragility analysis, and at the end, risk estimation. Let's start with experimental design. By experimental design, I mean a process in which we design virtual experiments to study the problem at hand. Here we are interested in the seismic response of the dry casks, and we want to consider the most important parameters. To do that, we have considered 12 parameters, mainly geometric and material parameters, as well as the weight of the cask and also the friction coefficient between the cask and its foundation. By using Latin hypercube sampling, I generated 160 configurations of this problem. I also performed an earthquake selection for the West Coast, Central, and East Coast. And we analyzed the configurations that I talked about subjected to the ground motion suite. For the analyses, I used the LS-Dyna. This figure shows one of my models in which I modeled the pad and the cask and its contents with solid elements, and the solid with discrete elements. The model is nonlinear in the sense that there's a contact between the cask and its foundation. Before running the model for probabilistic analyses, we needed to validate that against experimental results. There's a study in the literature performed by NHERI et al. They studied a scale cask on a 2D shake table test and reported rocking angle, displacement, and acceleration at bottom and top of the cask in one of their tests. And this is how my finite element results are compared with the experimental results. After validating the finite element model, we used that for the probabilistic analysis, and analyzed the finite element models, which gave us time histories of different responses. In this study, I'm interested in the rocking response and the horizontal displacements, and specifically the maximum values. So this figure shows the time history response from one of my analyses, and the value that I'm interested in is the maximum value. Running finite element models is usually time consuming, and it needs computational resources. And this was one of the motivations to develop metamodels, which I will talk about more later, because metamodels save time and computational resources. They can also be very useful for sensitivity analysis. So in this study, I have developed metamodels for the maximum horizontal displacement and maximum rocking angle. By metamodel, I mean a mathematical expression which predicts a target response as a function of input parameters, which we call predictors. For example, in this equation, y can be the maximum rocking angle, and x's, which are the predictors, could be the earthquake intensity measure, or the friction coefficient between the cask and the pad, or the dimensions of the cask. For metamodeling, I have used the response surface method. And when we fit a response surface model, we are looking for model parameters, which are shown by theta and model error. I have used a stepwise regression to select the best set of predictors and assessed the performance of the model by using 5-fold cross-validation. So reviewing the literature on dynamic response of rigid bodies, we see that the accelerations at the center of gravity of the body play important role in the dynamic response. This gave us the idea to develop a dual layer metamodel in which in the first layer we predict the maximum horizontal and vertical accelerations at the body's center of gravity. After predicting those accelerations, we can estimate two dimensionless parameters, which I show by RD and RR here. These dimensionless parameters predict the initiation of sliding and rocking response. And then we can use those parameters along with the accelerations and other parameters like friction coefficient, dimensions of the cask, etc., to predict the target responses of this study. I mean the maximum horizontal displacement and maximum rocking angle. So this is my model for the maximum horizontal acceleration of the cask's center of gravity. And if you look at the model, you see some terms like omega and p, which I will talk about later. And this is my model for the vertical acceleration and its performance. And at the end, the models for maximum horizontal displacement of the cask and maximum rocking angle of the cask and how they perform. The R-square of all the models is at least 0.88, and most of them are about 0.9. And now we move to the fragility analysis. By fragility, I mean the probability of a response reaching or exceeding a limit for a given set of predictors. For example, in these plots, I'm interested in knowing the probability of the maximum horizontal displacement exceeding a limit. I chose 1/4 of the cask's diameter as the limit. And each figure shows the probability of exceedance as a function of PGA, which I have used as the earthquake intensity measure for the set of parameters which are given here. As I mentioned before, we had some omega and p in the formulas. Omega is a parameter which tries to capture the frequency content of earthquake. and P is a parameter which is called characteristic frequency of the cask. So studies on rigid blocks and rigid bodies have shown that the dynamic response depends on the omega over P ratio. And in this study, we came up with two definitions for omega. One is omega A and the other one is omega P. Omega A tries to capture the effect of short period contents of earthquake, and omega V tries to capture the long period contents of earthquake. And our models show that for omega over P close to 1, larger responses are expected, which is kind of a resonance phenomenon. In both cases, I mean, when we look at the omega A over P and omega V over P, we see that the response increases when omega over P approaches 1. We can do the same fragility analysis for the rocking response. In these plots, I'm studying the probability of the rocking response larger than 1/4 of the critical angle of rotation. By critical angle of rotation, I mean the angle of rotation beyond which the cask falls. And the same trend applies here. I mean for omega over P close to 1, the response is larger and the corresponding probabilities are larger as well. As I mentioned before, the meta models are very useful for sensitivity analyses because they can be used for any given set of predictors as long as they fall into the ranges that the meta model was trained for. In this plot, I'm studying the sensitivity of the horizontal displacement to the friction coefficient. And as we expect for smaller friction coefficients, we want to see larger displacements, which this plot basically shows. For the smallest friction coefficient, which is 0.2 here, we have the largest probability of failure. The sensitivity analysis was also done for the rocking response. The rocking response is sensitive to more variables, including friction coefficient, the dimension of the cask, and the critical angle of rotation. If we look at the sensitivity to the friction coefficient, we see that for larger friction coefficients, we have larger probability of failure. And that's because for large friction coefficients, the cask cannot slide and the dominant mode of motion is rocking. And therefore, larger rocking motions are expected. The second parameter is the dimension of the cask. Studies on rigid blocks have shown that for geometrically similar blocks, the block with larger dimensions is more stable and experiences smaller angles of rotation. Same pattern applies to the casks. And for a cask with larger dimensions, we observe smaller rocking angles. And then moving to the critical angle of rotation for casks with larger critical angle of rotation, we see smaller rocking angles. This pattern also applies to rigid bodies. Another application of the fragility curves is risk analysis. We can integrate our hazard over the fragility curve to estimate the risk for any given location. In this slide, I have chosen seismic hazard curves from USGS website for a location on the West Coast, on central US, and then on the East Coast. And I have calculated this integral to estimate the annual risk for large horizontal displacement and for large rocking angles. If we look at the numbers which show the risk, we see that the risk is 1 order of magnitude larger on the West Coast, which is expected because of the seismicity of the region. And if I want to compare these numbers with acceptable limits in the nuclear industry, I compare them with core damage. So core damage is a metric which assesses an event in which the core of a reactor is damaged, but no release of radioactive material happens. The seismic response of the casks is similar in the sense that the casks might experience large motions, but it does not necessarily mean release of radioactive material. The acceptable annual risk for the core damage in the nuclear industry is 10 to power of -4. And for the set of parameters that we chose here, the rocking risk, the risk for rocking on the West Coast approaches that limit. And I should emphasize that it does not mean release of radioactive material, and to have a comprehensive understanding and estimate the overall risk, we need to analyze cases in which two adjacent casks hit each other because of large rocking motions and see what happens in that scenario. So this wraps up my seismic analysis part, and now I move to the tip-over analysis part. The tip-over analysis follows the same 5 steps. I mean, experimental design, finite element analysis, metamodeling, fragility analysis, and risk estimation. In the tip-over analysis part, I want to study the structural response of the cask, where it falls down and hits its foundation. The motion starts at the critical angle of rotation of the cask. In this problem, I have chosen a fixed geometry for the cask, so the geometric parameters of the cask do not change. And I have basically focused on the material variation in the cask, foundation, and soil. The only geometric parameter which changes in my problem is the thickness of the pad. I'm also interested in the cask's age. As I mentioned before, these structures have to be used for long periods of time. So age of the cask is another parameter which changes in my models. Since we considered the age of the cask as a parameter, we needed to update some material properties associated to that. As time passes, the temperature at different parts of the cask go down, and this plot shows how the temperature goes down at different parts of the cask, like the fuel basket, the canister, and the liner. And corresponding to that, the material behavior of these parts, which are made of steel, are affected. These two figures show how the modulus of elasticity and the yielding stress of these parts change in time. If you look at the modulus of elasticity of steel, you see that the main changes happen during the first 10 years of service, which I will talk about this more later. For the analysis of this problem, I have used Elestina, and this figure shows one of my models. I have considered the soil, the foundation, and the cask. So the cask has different parts. One is the concrete overpack, which is shown by blue here. It also has a reinforcement. And then the liner, the canister, and the basket. So the basket basically holds the fuel rods, and it's inserted into the canister, and the canister is inserted into the liner, which is sealed on top by lid. Before running this model for probabilistic analyses, I validated that against experimental designs. So our colleagues in University of Houston performed an experiment on a scale cask, and they released the cask from a 45-degree angle, and it hit its foundation. They reported cracking patterns and also vertical accelerations and stresses, which I will talk about now. In this figure, I'm comparing the damage patterns on the side of the cask. In the experiment, the cracks begin on top of the cask, and then inclined cracks develop towards the middle of the cask. And there's not much crack on the bottom. In my finite element model, I have used a continuous surface cap model for the concrete, which gives me the damage pattern, and it's similar to what we observed in the experiment. I mean, a concentration of damage on top and middle of the cask, and also inclined patterns of damage. Another parameter of interest in impact tests is acceleration. In this study, the researchers reported the maximum vertical acceleration. In this figure, I'm showing my results with the experimental results, and the average difference between the results is about 6%. I compared also my stress results in the rebars with the results reported from the experiment, and the average difference in this case is about 6% again. So after validating the finite element model, we used it for the analysis of the 200 configurations, and we again developed a meta model. For metamodeling, I used response surface method and stepwise regression for selecting the best set of predictors, and I evaluated the model performance by using 5-fold cross-validation. In an impact scenario for the casks, one of the main concerns is that the cask maintains its integrity, and we do not want to see any release of radioactive material. For that, usually in the industry, the main concern is on the canister, and we don't want to see any fracture in the canister. To study that, we have developed a meta model for the maximum strain in the canister, which I show here, and how the model performs. I should mention that fortunately, we did not observe any fracture in the canister, but we observed many yielding cases. In fact, in almost all the cases, the canister yields, but it does not fracture, which is good news. And we used this meta model for fragility analysis and sensitivity analysis because it gives us some idea about the variation of risk in time, and also how it is affected by different design parameters. So for fragility analysis, I chose a limit and developed a fragility surface as a function of the initial angular velocity and age of the cask. Looking at different cross-sections of the fragility surface, we see that the fragility increases with the age of the cask. It means aging increases the probability of failure. However, the main variations in the fragility happen during the 10 years, the first 10 years of service. And that's because the model that I showed takes into account the steel material properties. And as I mentioned before, the main variations of the steel material properties happen during the first 10 years, and the fragility curves show the same trend. The meta model was also used for sensitivity analysis, and in these plots I'm showing how the response reacts to variations in the compressive strength of the concrete in the overpack, and also pad parameters. Looking at the compressive strength of the overpack, we see that for a stronger concrete in the overpack, smaller failure probabilities are resulted. But when we look at the pad, any variable or any changes which makes the pad stiffer applies more forces or stronger forces to the cask, which lead to increase in the probability of failure. For example, if we use high strength concrete in the pad, the probability of failure increases, which is shown by the black curve here. And if we increase the thickness of the pad, it also makes the pad stiffer, and it increases the probability of failure. Another application of the metamodel that I showed is studying the aging effects on the cask. As I mentioned, the casks have to be used for long periods of time, and aging is a threat. In these figures, I am studying the ASR effect on the casks. ASR is a phenomenon in which usually the mechanical properties of the cask of concrete are affected, and usually the compressive strength, tensile strength, and modulus of elasticity reduce. So if we can combine studies on ASR effects on concrete with the metamodel that I just showed, we can update our fragility. And these are the results from 5 different studies on ASR. And as we see in all cases, the probability of failure increases for the ASR affected casks. And in the cases that the reduction in the initial compressive strength was larger increases observed. For example, in the worst case, which is the bottom left figure, the reduction was about 30% in the compressive strength, and at the end of the test, the compressive strength was about 70% of its initial value. And as we see, we have the larger jump in the probability of failure. Another application of the metamodel and the fragility analysis is the risk estimation. So we can integrate over the fragility and estimate the risk. This figure shows how the risk in the tip-over problem varies with time. And as we see, for older casks, we have more risk of failure. And the same pattern that we observed in the sensitivity analysis applies here. I mean, a stronger concrete in the overpack reduces the risk, but a larger strength for the pad, for the concrete in the pad, and also a thicker pad increase the risk. These plots suggest that from a design perspective, we should use concrete with high strength for the overpack, but we should reduce the strength of the concrete and the thickness of the pad as long as other structural criteria are met. So this wraps up my tip-over analysis, and now I want to talk about the role of HPC in research projects like mine. So this is the workflow that I showed you before, and I had to use high performance computing for running my models. In the seismic analysis part, I had about 500 models, and each of them took 3 hours at least on 96 cores. For the tip-over analysis, I had 200 models, and each of them took about 3 hours, again on 96 cores. And this means that without high performance computing, I was not able to do this research. The workflow that I usually follow to prepare my models and then analyze and post-process them is shown here. I usually prepare my models on my computer desktop, and then I submit them to a cluster, and then I transfer the results to my desktop computer again for post-processing. One cool thing about DesignSafe is that now this entire process is available on DesignSafe. Recently, a colleague of mine and I tested this process on DesignSafe. I mean, we created a finite element model in LSINA on DesignSafe, and then submitted that to Stampy. And then we did post-processing on the results. I know that DesignSafe people have been working on this, and they had some issues with the license. I'm not sure if the licensing issue is solved or not, but once that is solved, you can basically use DesignSafe for research projects like mine. Okay, so in conclusion, In this presentation, I talked about seismic analysis and tip-over analysis of vertical concrete dry casks. In the seismic analysis, I developed meta models for the maximum rocking angle and maximum horizontal displacement of the casks. These meta models can be used for fragility and risk analysis, or they can be used by other researchers or engineers for any given set of predictors. Looking at the risk, this study suggests that the risk approaches acceptable limits in the industry for the rocking motion. However, it does not mean release of radioactive material. For the tip-over analysis, we also performed a probabilistic study, and our finite element models show that fracture is not expected for the canister, which is good news. And we also performed a sensitivity analysis, which gave us some suggestions for design. To finish this project and estimate the overall seismic risk to the dry cask storage system, I still need to analyze the scenario in which two adjacent casks hit each other, and I want to know what happens in that scenario and if we have any fractures or not. At the end, I would like to thank my sponsor for supporting this project, and also RISE and DesignSafe for letting me use their high-performance computing infrastructure. And this is my email. If you have any questions or anything to discuss, just feel free to email me. And at the end, I would like to thank you, and I'll be happy to answer your questions.
That's great. Thank you, Majid. A very interesting presentation, and certainly a problem that will be around for a long time. At this point, we will open the question and answer session. Attendees, you're reminded that questions should be submitted through the chat panel and sent to the moderator. And I think we have a couple questions for you. I guess the first one might be pretty simple. Where are the casks located?
So these casks are located almost everywhere in the country, but the concentration is more on the East Coast. And there are some on the West Coast as well, but the main concentration is on the East Coast.
Majid, how did you characterize the ground shaking for the different regions?
So I performed an earthquake selection for the different regions, which I showed before. So I did earthquake selection for west of US, central US, and eastern US. And we had ground motion suites for each of these seismic zones. And we analyzed the 160 configurations that I showed subjected to each ground motion suite, which were selected for each of these regions.
Sorry, how many ground motions?
So we had 160 ground motions, and we paired them with the 160 configurations.
Okay.
But this was done for 3 different regions, so it gave us 480 models in total.
Okay. In the configuration of these casks, they're standalone, but how much space is there between the casks? And a follow-up question is there any mechanical, there isn't any mechanical tie downs to the casks, but is that considered at all or an option, or why isn't there?
The gap between these casks is 4 to 8 feet, which is 1.2 to 2.4 meters. The way these casks have been constructed is that they're not attached to the foundation. And the concern about the seismic motions have come up recently. And as I know, it's not allowed based on the standards to attach them to the foundation now. So that has been the traditional way, the conventional way these casks have been constructed.
Okay. And you mentioned a little bit about the vertical ground acceleration as a predictor for the maybe the PSDM development. Can you speak to that a little bit more?
So I tested different IMs for the earthquake, including the vertical acceleration of the earthquake, but it did not improve my meta models, so I did not use in the final meta models, but I tested its effect.
Okay. And maybe just one last question, since we're looking at the geographical distribution of the sites considered. And back to the hazard and how you characterized it, was there a different probability of tipping for the different regions, or is there a safer location for these to be centrally located?
So obviously, where we have a lower seismic hazard, the probability or the risk of failure is lower. Which I talked about here in the risk analysis section. So if you look at the risk at different locations, it's higher on the West Coast, and it's smaller for the central US and for the East Coast. So it depends on the seismicity of the region and how close is the casks to the seismic sources.
Okay. Well, again, thank you very much. We're at the conclusion of today's Early Career Researcher Forum. On behalf of the attendees, thank you, Majid, for taking the time to share this research.
My pleasure.
Yeah. And to the attendees, thank you for your participation and questions. Please check the SimCenter's website at simcenter.designsafe-ci.org and check your inbox for emails from announce@DesignSafe-CI. From there, you can find registration links to upcoming webinars in the Early Career Researcher Forum and the Natural Hazards Engineering 101 webinar series. Thank you for attending today's forum.